All right, let's get back to it then. So we were talking about the formal definition of a DFA, and I want to say a little bit more about that. Maybe we could just do another example here. So if this is a DFA, how about I'm going to use one of the examples we talked about last time. Something like this. Right, and I think last time the first one was accepted also. So this one will accept any string of the form a to the n, b to the m. This is the one which will reject if there's ever a after a b, although you can say a little more clearly it will accept all strings of the form a to the n, b to the n. Anyway, can we write the formal description of this DFA? Now, we need to give names to the states, so I will call them, and you can call them whatever you like, maybe X, Y, Z. Those are capital X, Y's, and Z's. Let's write the formal description of the DFA. If you ever see this on a test or something, it's very easy, provided that you remember how to do it, although you're going to have to write kind of a bunch of stuff, but there's nothing hard about it. I saw, once I asked the question like this on the test, I think this is also something that's so easy to do that you can kind of forget about it because it's not all that interesting. But I wrote, this is the question, and someone wrote like a very sort of, using very formal language, like this DFA has 3 circles and some arrows, very formally described. This is not what I mean. The formal description is a specific sort of mathematical description. So I would say it is this, M equals some bunch of stuff. And remember, there are 5 things, and they go in a particular order. The first thing is the set of states, which we called a big Q last time, but you might as well just write that set right in here. The set of states is X, Y, Z. That's the first thing that goes in the formal description. So this I will refresh our memory. This is the set of states. The next thing is the alphabet, which in this example is A and B. The next thing is the transition function, which is actually the sort of biggest part of this, which we always call delta. And I'm just going to write delta right there, and then down below I'm going to say where delta is, and we'll write some more stuff about delta later. Delta is so big it's impossible to cram into the thing up there. Anybody remember the next thing? So I'll just label these. This is the alphabet. This is the transition function. Trans function. Yeah, I can still talk about trans. It's not illegal yet. The starting state comes next. Yes, I'm dropping my hot takes here. She's just carrying on as usual. The starting state in this example is X, right? It's just one of those 3 things, and you can tell on the diagram it is X. And what comes last? Anyone remember? Yeah? The set of accepting states. So the last thing shall be written as a set, and it is X comma Y. Those are the accepting states. So this is the starting state, and this is the set of accepting states. Great. All right. And then to complete our description, we should write down what delta is. And this is kind of a pain, but the only way to do this is just to write out all the values of delta. I guess there will be 6 of them here. And remember the format, the way that we write the values of delta is delta takes a pair. The first is a state, and the second is an alphabet letter, and the answer is a state. And in particular, like, so for the first one, oh no, decline. Sorry, I get phone calls from the Red Cross all the time, and it's often around this time, so this may happen. I always decline. I don't want to talk to them. The bloodthirsty Red Cross. I donate blood fairly often, and they're on me. I got to do it at my own pace, you know. I'll come when I'm ready. Okay, when I write this, what that means is if I'm in state X and I read a A, then that goes to state X, and that's representing this looping arrow right here. And then we just have to write all the other values. So delta of X and B, the arrow from X with a B goes to Y, so that's a Y. Delta of Y and A, I got to do delta of Y and B. Delta of Z and A. Delta of Z and B. So delta of Y and A is Z. That's because the Y, from Y the A arrow goes to Z, so that's Z. Delta of Y and B is Y. Delta of Z and A is Z, and delta of Z and B is Z. And this completes the formal description of the DFA. All right, any questions about that? I hope you are in agreement that this is not really hard. You just have to remember how to do it. And you remember where everything goes, but there's nothing real fancy about it. All right, I will refresh our memory. So this is just something that I wrote last time, which, oh, sorry. Here, delta, if you recall, goes sort of Q cross sigma to Q. That means you plug in a pair, which always looks like a state, followed by a letter, right? And the answer, this Q over here means the answer is a state. All right, this is delta, and it's called the transition function. We are going to make use of a slight variation on delta. We also will consider what we call the extended transition function. The extended transition function is a function where you don't just put in a letter, but you can put in a whole string. It looks like, so that one would look like something like delta of X, comma, AAB. But we don't call it delta, we call it delta star, all right? In this class, generally speaking, the star represents iteration of some sort. And so what's the meaning of this? It means it's just like the normal delta, only you can put a whole string in it. And it means if you start in X and then you do this whole string, one letter after another, A, then B, then what state do you end up in? And in this, if I'm just still going off of this example here, sorry, I got to scroll way out, zoom way out. If I start in state X and I do AAB, it does AAB. The answer will be Y. So this, in my example, this answer is Y. So it tells you sort of the final destination if we read an entire string. Not just one letter, right? So the ordinary transition function, delta, just takes one letter in that second position here. But the extended transition function, you can plug a whole string into it, and it does that whole string one letter at a time. If you wanted to write the domain and the codomain, so delta star here, its domain still consists of a pair, where the first thing is a state, so it's a Q cross, but the second thing is not just a letter. The second thing is any string made up of letters. And the set of all strings is what we use the star for. This I think we talked about on maybe the first day or the second day. If you have a set with a star, that means the set of all strings using letters from that set. All right. And then its answer again is a single state, and so the answer when you do this delta is in Q again. Right? This is the extended transition function. All right, it's important, and you'll see why in a few moments. Could we discuss actually some simple properties of the delta star? You know, the function delta, really, delta can be any function. It has no real properties like, you know, There's nothing, you could make the values of delta be whatever you want, and it's still legal as a transition function. But this delta star function always obeys some, I will say, simple properties. The first two are very simple. The last one is a little crazy, but perhaps somebody can say, and this is not just in our particular example, but just for any example, can anybody say, what do you get if you do delta star of x and the empty string? What should this be? Yeah? X, he says. Yeah, why do you say that?
Because you're not doing anything, you're not transitioning.
Yeah, right. What this means is, if I start in state x, and then I read all the letters from the empty string, where does it end me up? And the answer is, if you're reading the empty string, then you don't go anywhere. And so the answer is just x. Excellent. That was the first of the simple properties. The second of the simple properties is, if A is a single letter, sorry, this is confusing. I mean the letter A is a single letter, then delta star of x and A is just the same as the old delta, right? Delta is the function which works on a single letter. Of course, you are still allowed to use delta star on a single letter, just treating this single letter as a string consisting of a single letter. Anyway, they are the same in that case, right? And the third property, and this one is important, and I would say those two properties are just straight up obvious. The last one is less obvious, and also going to be, we're going to use this last property fairly often. It is something like this. I'm going to see if we can fill in the blanks over there. So the idea here is, if I start in some state x, and then I read two strings one after another, read through x first, and then read through the string y, where do I end up? And I want to say something, don't write this down because this is not right, but I want to say something like this is kind of like starting at x and then reading the first string x, and then after that, you read the second string y, right? You kind of, if I say, I want you to read through the string xy, that's the same as reading through x first, and then from there you read through y, right? This is the idea. But that on the right is bogus. Can anybody say what's wrong with that? The idea here is first you do x and then you do y. That's what I want to say. Anyone dislike what I wrote over here? Yeah?
Will it not just become two states?
Yeah. If you think about, like, if you were to do each of these things, this is one state. Maybe this is like state y and this is z. So what's the answer here? Y, z? That doesn't even make any sense, right? There's no such thing as like multiplying two states together. So this is definitely not correct. Anybody have a better idea about how can we write this idea of I want to say you start in x, you do the first string x, and then from there you do y. You really cannot just you can't just put two deltas next to each other like that, right? Yeah, if you want to do one delta followed by another, the way to do that, since these are functions, would be to like compose them, put one inside of another. So the proper way to write this is somehow, so it's not that, it's more like delta star of something like that, right? And this, I haven't filled in the blanks yet, but at least this will make sense, because this delta star here, its answer will be a state. And a state is actually the thing you can plug into another delta star in the first position of this pair. So this at least will make some kind of sense for evaluating. Anybody want to say what should I actually put in here? If I want to start in state x and then do x followed by y, how should I fill in the blanks here? I left some stuff out. Maybe somebody else I haven't heard from. Any thoughts? How about what goes here? This is the first coordinate of this delta star. That should represent the state that you begin with. I think the only thing that could possibly go here is x, the state x. That's the only state that I'm talking about anywhere. So there should be a big X here. I hope the big X and the little x are not confusing. Anyway, this says you should think of this one as like what happens first when you write functions inside of other functions. You know, you do the innermost thing first. So I'm going to say first I start at state x and I read the first string, which is little x. And then whatever this answer is, I start in that state and I read the other string y. This is how I'm going to say it. So I will write this in a nice way here. Maybe just in case this is confusing, I'll use a S, just so you don't get the big X and the little x confused. It looks like this, and this is weird looking, but it is a very natural idea. And the idea on the right-hand side, you see this sort of inner thing. It says first, start in state S and read through x. And then the outer one means starting wherever this ended up, you read through y. That's how you should sort of interpret this whole thing. Then from there, read through y. Right, this is the idea. Very sort of complicated looking, I would say, but the idea is very simple. It's just weird looking when you use it. You will actually be using this formula. I don't know if you want to memorize this or put it in a box at least. You will, I suppose, like by the time this comes around on a quiz, you should have this memorized, I guess. Although once you are like sort of clued in on the concept, it's not so hard to come up with this again after a few seconds of thought. That is the appropriate formula to be using. All right, we can now state, this is the last bit of sort of formalism, then we'll move on to something a little bit different. We have talked about the formal definition of a DFA. We should also define formally what is L of M in terms of the formal definition, in terms of the formal description. All right? L of M, remember, is the set of strings which are accepted by the machine. It is the language accepted by the DFA. So when we say, I'll write it this way, given M as this formal description, this is usually what we call the 5 different ingredients here. And a string x in sigma star. What does it mean for that string to be accepted? X is accepted by M when, well, to say in words, it's accepted, it means if you start in the starting state and then you read the whole string x and you end up in an accepting state, then it should be accepted, all right? We can actually say all of that just using the formal symbols from this description right here. What I'm going to say, I'm going to try and write down, formally speaking, what I just said in words. If you start in the starting state and you read x, so the way to write that would be this, delta star q0 and x. That means starting in the starting state, which is q0, I want to read the whole string all the way through of x, and I have to use the delta star because x is a string rather than just a single letter. And then what do I say about whether this is accepted or not? This is accepted if the answer here is a state, and if that state is part of the set of accepting states, then it is accepted. And the way we write that is just this. So this is a very sort of compact way of saying that in ordinary language means x is accepted. Right? It says if I start in the starting state and I read through the whole string x, where I end up is one of the accepting states. That's how we write all of that. And so the definition of the language, you can write it this way. It's the set of all strings x in sigma star such that delta star of q0x is in F. This is classic sort of Hollywood style math. It looks completely nonsensical if you don't know what I'm talking about. But that is the formal definition of the language of the machine. All right, show your friends. Look at this crazy thing. They'll say, wow, you really understand all that? See, kind of. I hope you do. It's not that complicated. It just looks crazy. All right? Great. Let's, so the real purpose of all of this formalism is not just like to impress your friends at the library, but really it is so that we can prove things. So we need this formal description. We need this formalism in order to prove stuff about DFAs. Now, we're not going to do a whole lot of proving of stuff, like in general this semester, but this is, of course, very important. And it was like a real central concern to people like Turing, who were the first people to come up with these ideas. The real problem in describing sort of the whole basic idea that Turing and other people were trying to get at is try to describe exactly what are the capabilities of computing machines. And the immediate question that you would have if you're trying to describe the capabilities of computing machines, immediately the question will arise, what counts as a machine or not? And the answer is, I don't know. Like, there is not a good answer to that question in casual terms. But if you can somehow describe your entire machine in the language of mathematics and set theory, then that tells you what is allowed, what counts as a machine or not. And if you want to prove something about those machines, you must use this kind of formalized set theory. It's not good enough to just show people diagrams and point at the diagram as if that was like a proof of anything. It's not. All right, so anyway, that's the point of all of this formalism. And I said we're not going to spend a lot of time in this class proving stuff, but we are going to do it sometimes, and that includes today. So I want to talk about how to prove a DFA accepts this or that string. How to prove that a DFA accepts certain strings. These proofs that we're going to do, they are, I would say, individually not all that difficult. I don't know. It's like any kind of proof. You have to sort of learn the typical strategies. But one thing that is interesting about these is these are basically always, or almost always, I'm going to say, mostly, maybe always, proofs by induction. So this is something that I'm sure you all learned in your discrete math class. I don't know if you've done proof by induction recently, so I thought we would just sort of refresh your memory about how to do proof by induction. I hope that you remember a little bit. So how to do proof by induction. We're going to do everybody's favorite proof by induction. So this is just a little induction review. You did this in your discrete math class. It turns out, like, in actually this kind of like mathematical computer science, they use induction all the time. Like, everything is about induction in that kind of stuff. So here's a little induction review. Let's prove everybody's favorite proof by induction is this. If you ever learned how to do induction, this was probably one of the first examples. So let's prove this. This is a true fact about adding numbers together, and this is the standard thing that everybody does as a proof by induction. This is true for n greater or equal to 1. This formula only makes sense if n is greater or equal to 1. All right? There are two steps in a good proof by induction. Anybody remember the format here? What do you start with? The base case, yeah, this is everybody's favorite step, and it's almost always going to be very easy. So maybe I will start by saying proof. If people don't know, what you're doing here, you would sometimes say, I'm going to do this proof by induction on n, meaning n is the variable that I'm going to do the induction with. Okay, and a proof by induction always begins with the base case. The base case means you have to prove that the formula is true when using the smallest value of n that makes sense. And in our class, usually the base case will be n equals 0, although in this particular example, n equals 1 is the base case. You can see just right here, like this doesn't make a lot of sense if n was 0. So n equals 0 is not allowed in this particular example. Anyway, for the base case, you just have to prove that that formula is true when using n equals 1. And it just straight up is true. Maybe a simple way to write this would be just write out what is the left-hand side and the right-hand side of the formula that I'm trying to prove, this right here. The left-hand side, when I'm using n equals 1, just says 1, right? It's 1 plus, etc., up to n. But if n is 1, then that's just 1. And what does the right-hand side say? Okay, you work it out. It's 1 plus 1, divided by 2. That is 2 divided by 2, which is 1. And these two things are the same, which is what we wanted, all right? So we have demonstrated the two sides of the red equation there are equal, all right? So the base case is finished. Usually the base case is very, very easy. You just have to sort of plug stuff in and see that it's true. Okay, next comes the induction step, and this is the more interesting part. And in the induction step, you assume something or other is true. That's called the induction hypothesis, and then you have to prove that something or other else is true. And you may have written, different people write these induction steps in different ways, but I'm going to say it this way. I'm going to say, assume that the red formula up there, which is what we're trying to prove, I'm going to assume that that is true using a certain value for n, which I'll call k. So I'm going to assume 1 plus 2 plus, etc., up to k equals k plus 1 over 2, like that. And then we must prove that this is also true using k plus 1 instead of k. So I will say we want to show, I am also often going to abbreviate that as WTS, means want to show. I want to show that same formula is true, but using k plus 1. So that would look like 1 plus 2 plus, etc., all the way up to k, and then continuing to k plus 1 should equal the right-hand side if I use k plus 1 in place of k. So that says k plus 1, k plus 2 over 2, all right? For the inductive step, you assume that it's true for k, and then you must prove that it's true for k plus 1. And this right here, just a little terminology, that right there, this is called the inductive hypothesis, which I will often refer to with IH, the induction hypothesis. All right? You assume that that green thing is true, and then I must prove this other thing. All right, now let's actually do it. So usually we say some kind of words here. These are like throwaway words just to transition into the real proof. I haven't actually done any of the real proof yet. I'm just saying what I'm going to show. I start, for the want to show part, I'm just going to start with what it says on the left side. 1 plus 2 plus up to k, and then k plus 1. What can we do with that? I would say we can simplify stuff on the left side. Anybody see what can we do on the left side? You're allowed to do just like ordinary algebra steps, or you can, whenever you want, use the induction hypothesis. What shall we do on the left? Yeah.
You can substitute 1 plus 2 plus k for k plus 1 over 2.
Yeah, so I'm going to use the induction hypothesis immediately. 1 plus 2 up to k is equal to k times k plus 1 over 2. So this whole thing I'm substituting right there. It will say k plus 1 over 2, and then plus k plus 1. So I plugged in that step. I used the induction hypothesis. Sometimes when people want to be super clear about their proof by induction, they put a little IH on the equal sign, just as a signal. This is the step in which I used the induction hypothesis. All right? And now, hopefully, we can just kind of simplify this by ordinary means and end up with that. This is our goal. So can we resimplify here? I would say we want it to look like one big fraction, so I am going to add these things together. Maybe I'll distribute up there first, k squared plus k over 2. And then I intend to add those other parts into this fraction, so I'm going to make those into fractions with a denominator 2. Because I'm a good boy and I always make a common denominator before adding fractions. So when you add them, they look like this. Right? Remember, I have this right here is my goal. So I'm trying to simplify it until it looks like that. I'm starting to feel pretty good about this. Up here, I would combine the k's in the middle there. K squared plus 3k plus 2 over 2. And then factor on the top, and I think it looks like I wanted. Factor on the top. K plus 1, k plus 2 over 2. Done. All right? You can write something to indicate that you're done with the proof. I have this is my own stupid thing that I like to write. I have an old real analysis textbook from like the 19-teens, and they write that, "shoon," at the end of a proof. So this is what, you don't have to write "shoon" if you think it's stupid. I think it's stupid too, which is why I write it. All right, this is the end of the proof by induction. Can I just make one little stylistic comment? Notice that I did not just write this and then sort of simplify on both sides. I really don't like it when people do that. Simplify on both sides, and then you get down to something that says something like 1 equals 1, and you're like, yes, 1 equals 1. This is not really a good way to write a proof. I already know that 1 equals 1, so like that, write both sides and simplify both of them, don't do that. Start on one side, simplify it until it looks like the other side. Or if you like, you could start on the left side, simplify that, and then start on the right side and simplify that and show that they are equal to one another. That's fine. But don't write the same thing on both sides and work on both sides at the same time. That's bad style. Okay, I have just one similar proof by induction. I want to make sure that everybody is hip to the proof by induction before we try to do this for DFAs. So this is one sort of very similar kind of just basic arithmetic proof by induction. So I would like you to try prove that the sum of odd numbers adds up to n squared. This is for n greater than or equal to 1. All right, see what you think. It should be fairly similar. See if you can make it happen. I'm going to walk around and see how you feel. writing these, you should make it clear what parts are where you're assuming something and what parts are where you're actually proving something, just so that you keep it straight. Yeah, and also it's sort of the original statement is that should be which it doesn't have to be, but still good. You should replace the exact process is just the same as the AUK. And then what you want to prove is right next, which is like this, but going into K plus 1 instead of K. So the right hand side will say K plus 1. So here it's just K. Okay. Still good here? Good. I can start writing mine. I give you till the clock says 1:44 and then we'll talk about them. Although it seems to be going pretty well as I walk around.
Oh, because you're telling me second. Okay. That way the two will distribute. Yeah. Okay. Okay.
This is good, yeah. And now we can use the revision process. Good. Okay, let's talk about it. It says 144. So this is the induction hypothesis right here. And then what I want to show, you got to be careful and make sure you get all the little details right. But this is the induction hypothesis. What I want to show is this thing written again, but using k plus 1 instead of k. So I write all of this stuff, and then I go one more term, just directly like that, but using k plus 1 instead of k. And then on the right-hand side, I use, again, k plus 1 instead of k here. All right? So this is what I want to show. I'm going to start with the thing on the left, 1 plus 3 plus 5, etc. 2k minus 1. And then, well, I'll just write exactly like it is. 2k plus 1 minus 1. Can we simplify that? Well, first of all, we can use the induction hypothesis on the first part of it, right? That much is what I see on the left side of the induction hypothesis. And so this, using the induction hypothesis, is k squared, right? And then this, maybe I will distribute the 2 and do a little business over there. 2k plus 2 minus 1, right? So this is k squared plus 2k plus 1. And wouldn't you know it, that really is k plus 1, the whole thing squared, if you factor it. I hope that you got something like that. It's easy to mess up the details here when you're plugging in the k plus 1 business. Actually, I'll say in the proofs that we're going to be doing, I'm not going to say they're easier than this, but at least they don't involve big formulas like this. They involve formulas with like the deltas and the delta stars, because we're going to be doing this about DFAs. All right? Sorry, I'm looking at my clock. Any questions about this? I should put my shoe on the bottom there. Oh, look at that. Isn't that cute little curly? I didn't intend for that. Very cute. Should have that tattooed on my ear or something. Doesn't that look crazy? All right. I'm just riffing now because I'm not sure if I want to actually get into the details. So I want to do some proofs by induction using or in the context of DFAs. Maybe I will just sort of introduce one, and then we'll really do it for real next time. So we are going to prove when strings are accepted. And I think we should just go back to maybe the very first example of a DFA that we ever did was this. All right, this is a DFA which accepts strings like a to the n where n is even, right? This accepts a to the n where n is even, right? I want to prove that, okay? So if you ask me, like informally speaking, why is it even, I will say something kind of silly like, well, if you start here and you go bop, 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 then if it's even, you'll end up back here and it's accepted. This is not a good proof though, right? So this is why all that formalism is necessary, because without the formalism, all you have is like pointing at the diagram, which is not a good way to go about your life. So let's try and couch this all in formalized terms. So one thing that will make this a lot easier to deal with, rather than saying a to the n where n is even, it's actually easier to say it like this. It accepts all strings a to the 2n. That's just an easier way to frame what I'm talking about. Rather than saying a to the n, where n is some even number, it's easier to just say it like that, a to the 2n, where n is any number. All right? So that's one thing. But now we should write this in more formalized terms. What I want to say is a to the 2n is accepted. If I want to say this more formally, I would give names to these states. Maybe I'll call them S and T. Formally speaking, and this is what you have to do, like when you're doing these problems on the homework or whatever, you are going to have to translate the scenario that's written usually in words, kind of like this. You have to translate this into a formal statement using the deltas and whatever. Formally speaking, what I'm trying to show is, I want to show that delta star of S and a to the 2n equals S, all right? I hope that you can make some sense of this. What I'm saying, this is saying in these sort of formalized symbols, if I start in state S, which is the starting state, and I do a to the 2n, you have to demonstrate that you actually end up back in S, which is the accepting state. All right? And then how do you prove this? Prove this by induction on n. Right? And this we'll do next time, but maybe I could just talk through, first of all, you would do the base case, which is when n is 0. The base case would say delta star of S and a to the 0. But a to the 0 is the empty string. And so this will say delta star of S and the empty string equals S. But this is a basic property, one of those 3 easy properties of the delta star function that I said before. Delta star of X and the empty string is always equal to X. So that's the base case. And then the induction case, you have to do, I would say, slightly fancier thing, but we'll get into that next time. All right, I think that'll do for today. So next time we will begin with the quiz. The quiz, you should expect 2 questions, very similar to 2 of the homework questions. And then we will just go right on with the rest of class. Let me know if you want to talk about the homework now. I would be happy to.